Good afternoon, everyone.
Hello,
Welcome back. Hello.
am I audible?
Yes, sir, you are audible.
Oh, thank you. Thank you. Carry on.
Okay, sir. Welcome back, everyone, to our second session of IGNITE 2020. I would like to take this opportunity to thank our professors for guiding us for the organization of this online event. I urge all the participants to keep their cameras and microphones off during the session. The participants can write their questions in the chat box of Webinar Live chat box or in YouTube Live chat box, or during the last 15 minutes they can put their question in our Telegram chat box also. If any guest or participants wish to interact with our speakers, both the speakers, or say a few words about them or few words about the whole event, they can say about it. Please let us know in the chat box, and we will unmute you and you can share your thoughts there at the end of the session. Now, in this afternoon session of IGNITE 2020, an informative lecture will be delivered by our Honorable Professor Dr. Biswajit Ghosh on mantle melting. We all are delighted to have him amongst us in IGNITE 2020. Earlier, Dr. Ghosh has worked at Geological Survey of India and also has experience working as a geophysicist in Central Groundwater Board. Currently, he is a professor of igneous petrology at University of Calcutta. He has been rewarded many times for his excellent works by several prominent institutions like Asiatic Society, Japan Society for Promotion of Science, Central Groundwater Board, Geological Mining, and Meteorological Society of India. To name a few, Dr. Biswajit Ghosh is also a fellow of JSPS of Japan as well as West Bengal Academy of Science. He has written many research articles in collaboration with Indian and Japanese geologists. His research works are regularly published in popular journals like International Journal of Earth Science, American Mineralogist, Journal of Asian Earth Science, etc. The core area of his research is ophiolite. Dr. Ghosh has a significant role in the analysis of ophiolites from Andaman and northeastern India. Mantle melting is one of the most important phenomena of this dynamic planet and one of the most famous topics among the geologists as well. So, a session comprising of lectures on this topic from an expert is definitely going to be enjoyable for us. Mantle melting, where and how? Now, I would like to request sir to say a few words before moving to the main lecture session. Sir, over to you.
Thank you, Deepmala, for your nice words. And to the audience, thank you for your interest in attending this webinar, especially this talk. My today's talk is all about some basics of mantle melting. Before I start, let me tell you how this topic came into my mind. Just 4 or 5 days back, I received a phone call with a request. Sir, on Teachers' Day, we'll be arranging a webinar almost for the entire day. TV sir has kindly agreed to give a talk in the first half. Could you please give another talk in the second half? Till that time, I didn't have any idea about what it is going to be. To me, it suddenly came as a surprise. and that too at a moment when I was attending some repair work of my vehicle in the garage. So my immediate reply was, look, I am not a I am not good for a talk on Teachers' Day. Then I suggested few names, which in my opinion could have been better for this event. From the other side, the reply came, why not, sir? Since there will be many BSc first year students, why cannot it be on phase diagram? A subject I deal with in the master's first semester class. My immediate reaction was, no, this cannot be a talk on Teachers' Day. Moreover, even if I am good in teaching phase diagram, I cannot wrap it up in 1-2 hours talk. So conversation went on. By that time, I have decided my answer, but I was hesitating to tell it directly. Suddenly, a latest animation related to today's topic, mantle melting, came into my mind, which I thought is best to share with you today, especially those who are new entrants to this subject. I mean the BSc first year students. I don't know whether I should be called a speaker today because the content of almost the entire talk is made from snapshots taken from one animation, except little changes here and there, and describing it in my own language. In that sense, I may best be called a facilitator. So with profuse thanks to the organizers again and again, here it is. Let me share my screen now. Just 1 minute. Hope I am audible, huh?
Yes, sir, you are audible.
Oh, the things are really getting better. This was the picture in July. I'm sure in September things are far better. Okay, so moving on to the topic. Today's topic is mantle melting, where and how. Just a little moment. Because I need a pen. Can somebody please guide me how to get that pen or the indicator?
So your file is not yet shared.
Oh, I'm sorry. Is it shared now?
No, sir, the screen is loading.
No, not
Yes, sir,
yet.
now it's.
Meanwhile, can
I
you
can see
please
your
help me
window.
how?
The file is not on. So, the plus sign. Please go to the plus sign.
Yes.
Yes, sir. You
Okay.
can see the screen.
Okay. Okay.
And then
You can
share.
see the screen now.
Mm. So I can see your live webinar screen. You can go to the
Oh
PPT.
no.
It is okay, sir. The screen is being
Yeah.
shared, but go to the PPT.
Yeah. Yeah. That I will go. But I was just looking for a pen. That indicator.
So make this full screen once.
Okay.
Now on the corner you will find.
No. Once I make it full screen. Okay.
Whiteboard. No, sir. Can you find it?
Not this one. Oh no. Just a minute. Yeah. I got it. Hey, thank you.
Yes.
So, okay, moving on to the topic. It's mantle melting, where and how. So, whatever I'll be speaking, there will be nothing about the composition of the magma and how it changes. So, nothing sort of magmatic evolution. So, I will emphasize mainly on the process that operates in the Earth's mantle, in the shallower part of the Earth's mantle. So, consider our Earth as a internally layered structure. So we have very thin outermost crust here, and then here it's the core. Again, it has inner core and outer core, and the remaining part in between crust and core, it's the mantle, which is again divided into upper mantle and lower mantle. Then upper mantle again, it is divided into lithosphere and asthenosphere. I'll come into it later. But the today's entire talk is focused on this. Up to this depth, this blue line is indicating maybe around 200 kilometers. So this entire talk today is all about this 200 kilometer of the Earth's mantle, because this is the place, this is the region where mantle melting takes place. And further, let me tell you one more thing. So, because beyond that, most of the evidences are indirect. But up to 200 or 300 kilometers, we can sample the mantle either maybe in the form of xenoliths or something else. So anyway, if we zoom this 200-kilometer part of the Earth's outer surface, we have crust at the top, and below that it's entirely the mantle. As I told you, the upper part of this mantle, upper part of this upper mantle is called lithosphere, which is that together with the crust forms the lithosphere, and below this is a asthenosphere. So there is a drastic compositional difference and difference in terms of rheological properties of materials between this lithosphere and asthenosphere. In the lithosphere, the heat transferring mechanism is mainly by conduction, whereas in asthenosphere, the heat transferring mechanism is by convection. Now, if we put a scale here, so as I told you, today's entire discussion will be limited up to this 200 kilometer depth, and our lithosphere asthenosphere boundary is at depth of around 100 kilometers. It could be some places. And on the right side, this is the pressure axis. So at 200 kilometer depth, you can expect a pressure of 6 gigapascal. Whereas at the lithosphere asthenosphere boundary, it's almost around 3 gigapascal. And we can convert this depth versus pressure, and the gradient comes for each 33 kilometer depth, there will be 1 gigapascal increase in pressure. Now, if we plot the temperature within the Earth's interior, we will find the locus of that point. It forms a curved sort of thing, which in best approximation we can visualize this curvilinear thing as two straight linear parts with a kink at a depth of around 100 kilometers. And we call this line as the geotherm. So each point on this line will give you the ambient temperature at that particular depth. So at around 100 kilometer, you can calculate the ambient temperature here on this geotherm line. So I repeat, this lithosphere asthenosphere boundary is almost at 3 gigapascal, or in depth equivalence of 100 kilometer within the Earth. Now you see there is a change in slope between this part and this part. Here the slope is much gentler. That means with depth the temperature rises sharply. But here the slope is very high. That means it's almost of a constant temperature. But if you look carefully, it's not strictly perfectly vertical. That means with depth there will be little rise in temperature. But in this part, with depth there will be a very sharp rise in temperature. And accordingly, if we calculate the temperature gradient in this part, it comes around 15 degrees centigrade per kilometer. Whereas in this part, where the steep is high, it comes around 0.5 degrees centigrade per kilometer on average. And accordingly, this part is called conductive geotherm for the lithosphere, whereas this part is called adiabatic geotherm, which stands for asthenosphere. Now, we have already coined a term called adiabatic geotherm. So with a little pause on this discussion here, I'll move on to some basics of some school living studies in the next slide. So here, this is a PV diagram. This axis is the pressure increasing that way, and this axis is the volume. And now if we plot the temperature contours on this diagram, they look like this. So easily one can say for a constant pressure, since this side volume is increasing, that means this red line must be a higher temperature contour line. So here you see it's 600 Kelvin, 400 Kelvin, 200 Kelvin, accordingly like this. So on a PV space, this becomes the shape of the isothermal lines. In the same PV space, suppose this is one isotherm, higher temperature isotherm, and this is lower temperature isotherm. Now, if we join 2 points, one from this isotherm to another from this isotherm, this is a path of expansion because you see volume is increasing. But this path is no more isothermal paths. These are called adiabatic paths. So why I am telling, because I have already introduced the term adiabatic in my last slide. So any matter moving along these, it must be following a adiabatic process. So moving on to our famous Carnot cycle. Here you see this is the similar to this. This is a high temperature isothermal path, and this is again another isothermal path. But these two lines, these are adiabatic paths. So accordingly, from 1 to 2, we can call it isothermal expansion because volume is increasing. And from 2 to 3, this is adiabatic expansion. Similarly, this is 3 to 4. This is again following an isothermal path, but here it is compression. So this is isothermal compression opposite to isothermal expansion here. And here, this is adiabatic compression. So this is the entire Carnot cycle. And these two are, as I told, these are the isothermal pathways. So here to maintain this temperature constant, you need to supply heat to the system. And in the same analogy, from point 3 to 4 on this PV space, since it is an isothermal compression, you have to extract heat from the system to maintain a constant temperature. But on the contrary, 2 to 3, which is an isothermal adiabatic expansion, and here this is another adiabatic path. Here, in these two paths, the system behaves almost like a closed system. That means there will be no exchange of heat between the system and the surrounding. Only you need to supply heat, or you need to involve some heat here and here. In one case, you have to supply heat. In another case, you have to extract heat from the system. Just keep in mind, this is done only for maintaining the constant temperature in these two paths, 1 to 2 and 3 to 4. But in these two paths, there will be no exchange of heat between system and the surrounding. So in adiabatic process, we have to visualize these in our Mantle system as well. So moving on to my topic again. So this is a conductive geothermal gradient, average value 15 degrees centigrade per kilometer. And here it is the adiabatic geothermal gradient, 0.5 degrees centigrade per kilometer. Now you see the slope of this conductive geotherm is a function of the lithospheric thickness. How I will show you here. You see here, in this case, the lithosphere-asthenosphere boundary has been brought down to 150 kilometer. But you see, between these two cases, there is not much change in the adiabatic geotherm. The slope of this conductive geotherm is changing. For a higher lithospheric thickness, it becomes 10.3 degrees centigrade per kilometer in comparison to a general scenario where it is 15 degrees centigrade per kilometer. And now, if it becomes thinner, like this, the lithosphere becomes thinner. Here it is, you see the geothermal gradient is much higher, 21 degrees centigrade per kilometer for the conductive geotherm. But look at this adiabatic geotherm, it's almost the same line with the earlier. Hello?
So may I interrupt you for a minute?
Sure.
So can you hide the stop sharing bar that's coming at the bottom of your screen?
Oh, sure. Thank you.
Thank you. Sir.
Okay now?
No, sir.
Is it okay?
No, hide. I asked you to hide it. You closed the PPT.
Oh, really? No, I have not closed the PPT. It's moving now.
It's not being shared anymore on the screen.
Okay, sorry for the interruption. Is it okay now?
No, sir. It's still loading. Yes, sir. No.
still. Just
yes, sir, now it's coming.
okay, okay, okay. What I need to do now, full screen. So, resuming again, it's okay now? Okay. So, here you see
Yes, sir.
the conductive geotherm for this lithospheric thickness, that means 150 kilometer. The conductive geotherm value is 10.3 degrees centigrade. But if we lower the lithospheric thickness, the geotherm becomes much more higher. That means 21 degrees centigrade per kilometer. And for further lowering of the thickness, that means if we project the adiabatic geotherm up to the surface, it hits at a point where it cuts the 1400 degrees centigrade on the temperature axis. This is called the mantle potential temperature. So simply, what you need to do, if you project the adiabatic geotherm, the point where it hits the temperature axis, that is called the mantle potential temperature. So once we say that the mantle potential temperature is high, that means you need to think of this adiabatic geotherm is shifted towards the right hand side. And once we say that the mantle potential temperature of any region is low, that means the adiabatic geotherm is shifted towards the left hand side. And depending on the lithospheric thickness, the slope of this conductive geotherm varies. But the gradient of the adiabatic geotherm is almost unchanged. It is 0.5 degrees centigrade per kilometer in all the cases. So here the mantle potential temperature is 1410 degrees centigrade. Now, on this frame, if we plot the fast melting temperature of peridotite means that's the major rock constituent of mantle, that's the only rock constituent of mantle. So if we plot the fast melting point of peridotite, that is called the solidus points. So that you get a line like this. That means you go to this depth, the ambient temperature there is this, but the rock there is having a melting temperature which is this. So you see everywhere up to this 200 kilometer, this fast melting temperature is higher than the ambient temperature. So what does it simply tell? It simply tells that there is no melting in the Earth's mantle. And from the solidus line, what we understand, as I told you, this is a peridotite solidus. So anything towards the left-hand side of this line will be solid. But on the right-hand side, everything will be molten, at least partially molten. Unless there is another line, we call it liquidus. Beyond that, everything is completely molten. So between the solidus and liquidus, everything is partially molten. If we plot the liquidus here, it will come somewhere like here. So here my point is, go anywhere within the Earth's interior up to this depth, you will find rock whose melting temperature is higher than melting temperature, higher than the ambient temperature. So it simply tells there is no melting up to this depth. But at the same time, we can directly witness in some particular tectonic events that there is some melting within the Earth's interior. For example, the Mesoceanic ridge magmatism, for example, the subduction zone magmatism, earth volcanoes. So now I will discuss about the three great ways to melt this mantle. So now up to this point, it is very clear that once we want to melt the mantle, there has to be an intersection between the geotherm and the peridotite solidus. So let us look at the three great ways how we can melt the mantle. One is here, the mantle plume. The next one is the case of divergent margin. And the third one is the case of convergent margin. We will look into detail each one of them one by one. So first in the case of plume setting, this is the normal geothermal gradient, and this is the peridotite solidus. So once there is an involvement of the plume, as I told you about mantle potential temperature, what happens because of the influence of the upcoming plume from the bottom, the mantle potential temperature increases. What happens, you see, this line just shifts towards the right hand side here. And the moment it comes here, you see there is an intersection between this peridotite solidus and this geotherm now. So in this region from here to here, now you see the melting temperature of the rock is here, but your ambient temperature is somewhere here. So that means in this region, there will be some mantle melting. So this is the addition of heat from a mantle, which is shifting this adiabatic geotherm towards the higher temperature side, causing an interaction between the geotherm and the peridotite solidus. So melting in this region corresponds to melting here. Next, I will show you the distribution of this mantle plume, global distribution of this mantle plume. You see here it is afar. This is the East African rift system. Here it is another, you might have heard, you all know about Hawaii. Here it's Iceland. So these are the famous mantle plumes, present mantle plumes. And these are the distribution where they are located. So next I will come to the second case, that divergent setting. That means Mesoceanic ridge setting. So this is the normal geothermal gradient. So in every case, I will compare it with the normal geothermal gradient first. So here is the normal geothermal gradient. But in case of divergent setting, what happens? This lithosphere becomes thin enough. You see, the adiabatic geotherm is almost at the same place, but lithosphere is becoming very thin here. As a result, there is a high conductive geothermal gradient, 155 degrees centigrade per kilometer. And not only that, the important one is the interaction between this geotherm and the peridotite solidus again, because of this thinning of this lithosphere. So that means the asthenosphere is coming up, mantle is upwelling. And there will be interaction between these two. And in this region, you can simply see that the mantle is undergoing melting. So this is called decompressional melting. As I showed you in that Carnot cycle, it is just like that, following the adiabatic expansion or adiabatic decompression path. So in this region, there will be melting, and melting here, this is a very famous. You all know about this triangular region below the mid-oceanic ridge system. So melt field here corresponds to this triangular part below the mid-oceanic ridge system. So moving on to the global distribution of the mid-oceanic ridge system. Here is a map. So almost the central part of all the oceans is occupied by this system. So we have Central Indian East. We have East Pacific rise. We have Central Indian Ridge. We have Mid Atlantic Ridge, and so on. So third setting is a subduction setting, and the cross section looks like this, and this is the downgoing slab, and this wedge-shaped part above it is called mantle wedge. And what happens once this slab starts to subduct below this wedge, it gets dehydrated and it releases a lot of water and volatiles to this mantle wedge. That causes a lowering of the solidus of this rock in this region. So the solidus will no more lie here. In this case, below this divergent setting, this geothermal gradient will look like this, but in this case, this solidus will shift towards the left-hand side in the form of this. So this shift is just because of the lowering of the fast melting temperature of rocks in this mantle wedge. As a result, what is happening, again, there will be the intersection of these wet solidus. Now we will call it a wet solidus, intersection between this wet solidus and these geotherms, and that will cause melting in this region. And we call it flask-induced melting or flask melting in the subduction zone. So among the two dominant or two end-membered plate boundary system, one is the mid-oceanic ridge system we have seen earlier. Here it is the convergent boundary system where the melting mostly occurs because of the flask deriving from the subducted slab and causing a lowering of the melting temperature of the rocks in this region. So it's a thumb line that mantle melting in the subduction zone is a flask-induced melting. On the contrary, mantle melting below the mid-oceanic ridges, that is called a decompressional melting. Why decompressional melting? Because as I told earlier, the lithosphere asthenosphere boundary is becoming shallower. That means asthenosphere is coming up. So it's a case of mantle upwelling. So why this upwelling? Because it's a divergent tectonic setting. The rocks which are under tremendous pressure, they are getting decompressed and as a result coming up. So if we see the distribution of the subduction system, modern subduction system, here it looks like on the global map. So the entire talk today, as I told already, that it has been taken from animation from this University of Texas. And this is all about what I wanted to say today. So there is nothing about, as I told you, the composition of the magma or magmatic evolution that I wait for an opportunity, maybe the next webinar. Thank you.
Sir, please wait for some questions.
Sure.
Participants, please write your questions in the chat box or in the Telegram group.
Thank you, sir, for such an illuminating and eloquent session that would be helpful for us in our future, and it would help us in understanding of the subject. Now, there are some questions I have we got. Just a minute, sir.
Sure. Actually, nobody expected that this would be only for half an hour at the most. Because as I
Yes,
told
sir.
you
We
earlier,
expected it
I
to be
am
a
not a
1 hour session.
I expected, I told you perhaps earlier, I am not a speaker who can speak at length.
Okay,
I'm
sir.
sorry for that. And the later part, actually, I didn't want to involve it in today's talk because once I start the composition of the magma in this tectonic setting, it will be really lengthy in that case.
Okay, sir. Okay, there are a few questions. Can I? Okay, sir. The first question is from Anirban Ghosh. He has asked, why only consider the peridotite solidus and not other solidus such as dunite?
Yeah, because you see, the majority of the mantle lobe, it's peridotite, and dunite is volumetrically not so abundant. And this is one reason. And even though if you consider dunite, I don't think the scenario will differ much. So in that case, even in normal cases, the solidus will be on the higher temperature side like this. The solidus will be on the, because dunite will certainly have a much higher solidus temperature. So it will be on the more right hand side on this diagram. And in some particular tectonic setting, there may be interaction between this geotherm and that solidus. That may cause melting. But let me tell you, because in present day, means in Phanerozoic, it's really difficult to melt a diminutive protolith because that really needs a very high temperature. And our present geothermal gradient doesn't support that high temperature to melt a diminutive protolith. So, with all probabilities, the solidus of that diminutive protolith will be always towards the right hand side of the geotherm, and it will be difficult to melt it in any tectonic setting.
Okay, sir. Sir, our next question is from Shayan Maiti. Sir, any possible reasons for the accumulation of melted plumes, hotspot regions, mainly in the southern part of the equator?
So actually, this is nothing. This answer has no direct link with today's topic. Maybe it's a topic that should be dealt in geodynamics. I'm not sure, but honestly, I don't have any answer.
Okay, sure. We are moving on to the next question. The next question is from Bhaskar Ghosh, our respected VG sir. He has asked, in the case, which material actually melts
Bitwala,
the...
Bitwala,
Yes, yes.
let Bijis sir say it himself, if it's
Okay,
okay.
okay. Sir,
Okay, let me
okay.
be a little bit clear. Since I talked about melting in subduction zone, that is the third case. Okay, let me tell Bhaskar that this mantle wedge after receiving the flask from the subducted slab, they get metasomatized. And there will be development of lot of phyllosilicate minerals like phlogopite, like amphiboles in this peridotite. And the normal peridotite, which doesn't contain any hydrous mineral, but after metasomatism, it will become phlogopite peridotite or pargasite peridotite, something like that. That means there will be a dominant hydrous mineral in its mineralogical composition. And if you consider the solids of that phlogopite peridotite or pargasite peridotite in comparison to dry peridotite, this phlogopite peridotite is have a much lower melting temperature. That is why here I have considered this wet solidus because the rock here is no more dry peridotite, so we should consider the melting point of wet peridotite. That means this melting point. And this melting point you see is towards the lower side of the geotherm. That means the ambient temperature there will be higher than the solidus temperature of that wet peridotite, and as a result, it will undergo melting.
Hello.
Hello.
Deepmala, continue with the
Yes, sir.
question because I think Sir's mic is not working.
Yes.
My
Sir,
mic?
No,
no.
BG Sir's
Oh,
mic.
okay.
Should, is sir is there? BG sir is there?
Yeah, I'm very much there. I can hear you.
Sir, we are
A
we
much
welcome.
ahead.
No, sir. We welcome our respected sir Bhaskar Ghosh of Jogumaya,
His
Professor
mic is not working, Deepmala.
of. Hello.
Deepmala,
Okay.
BG Sir's mic is working, so you
So
can read out his question.
okay, okay. Actually, I have read his questions already. So should
And
I move to the next question?
now,
Has it been answered?
was my answer was enough? Whether I could attend it? What was
Sir
the
is typing.
question?
Yes,
Yes,
sir.
sir.
Sir is
Yes.
typing.
Thank you.
Yes, sir. Thank you,
Okay,
sir.
okay,
Okay, sir. Sir, should we move to the next question?
sure, you should.
Okay, sir. So the next question is from Shagnik Sharkar. What happens in melting when ridge system coincides with mantle plumes, like in islands, Iceland?
Oh, in that case, actually, you will have combination of this first and second. So, what will happen?
Yes, sir.
So, as I told you here in this reach system, what happens? Lithosphere, there will be asthenospheric upwelling, and in the plume system, what's the difference? The difference in the plume system, what happens? The mantle potential temperature becomes higher. So, in a tectonic setting like Iceland, you will have combination of these two. So that means your mantle potential temperature will become higher, as well as there will be thinning of the lithosphere. So the picture will be something like a combination of these first two cases.
Okay, sir. Thank you, sir. Next question is from Manoj Ranjan Swine. He has asked, sir, how spinel minerals groups are formed in upper mantle zone?
Yeah, actually, I have blanketly named the rock as peridotite in mantle, as a mantle rock. But again, if we look into the mineralogy of this rock, the silicate constituents are olivine, OPX, CPX, but there is an accessory phase which is a high aluminous phase, and The stability of that accessory phase is depends on the depth where the peridotite belongs. That means at the shallower level, that this high aluminous phase will be plagioclase, and the peridotite should be called as plagioclase peridotite. And if you go below, the plagioclase will not be stable anymore, and that will be converted to a form called spinel. And the reaction I will tell you later. So plagioclase peridotite will be converted to spinel peridotite, and beyond a certain limit where spinel becomes unstable and it transforms into garnet. So spinel peridotite then transforms into garnet peridotite. So what happens in case of suppose a garnet peridotite is getting exhumed? So your dominant mineral composition in that garnet peridotite is olivine, two kinds of pyroxene and garnet. That garnet and olivine will react and it will form orthopyroxene, clinopyroxene, and spinel. And once it goes beyond the limit of this garnet stability field, that means once this reaction starts coming, it is the region of the spinel peridotite. And up to a certain depth, that spinel peridotite becomes stable. And in the shallower part, again, the spinel peridotites this transform into plagioclase peridotite by reaction, orthopyroxene, clinopyroxene, and spinel that will give rise to olivine and plagioclase. And your spinel peridotite will convert into plagioclase peridotite. Am I clear?
Yes, sir. I think he has got his answer. So, sir, the next question is from Kishan Sharma from Central University of Kerala. How we get the peridotite solidus line?
Oh, yes. Okay. This is a locus of the fast melting temperature with depth. So suppose at this depth, you have a peridotite whose melting temperature is here. So you make a point here, go up to this depth, and you again have peridotite, but the melting temperature of that peridotite increases here because of very obvious reason that because with increase in pressure, that means with increasing depth, the phases become more compact and you require very higher amount of energy to break those bonds. So that is why a rock, same rock at higher depth will have higher melting temperature. So by the word melting temperature, we should always mention at what pressure condition you are asking it. So the same peridotite has a melting temperature at this depth here, but if you go at this depth, the melting temperature becomes here. And if you join this melting temperature means I am talking about the fast melting temperature. That means under any thermodynamic system, you are supplying heat to the system and the peridotite is undergoing melting. There will be a temperature where the peridotite will first start to melt. We call it solidus temperature. So once you plot the solidus temperature with depth, you will get a line like this. And you see, the first melting temperature with depth is becoming higher because of this obvious reason that melting temperature of the same rock with pressure is increasing.
Thank you, sir. Sir, can we move to the next question?
Sure.
So the next question is from Shayantani Chatterjee, Niigata University, Japan. The question is, we get hydrous mineral like amphibole in gabbros formed in MOR. What could be the source of hydrous magma in MOR? Since apparently it looks mantle beneath MOR is dry, what is your opinion?
Maybe a possible reason is in the magma chamber, if there is a collapse of some mantle rock, and in that region, the mantle rock will be in the form of serpentinite that is already hydrous. that is serpentinite or serpentinized peridotite. So once that roof collapses in the chamber, and it will add some water into the system, and the dry basaltic system will become a little more hydrous, and which on crystallization you can expect some amount of primary hydrous mineral like brown amphibole into the gap even. Otherwise, ideally, the system below the mid-oceanic ridge it's occupied by anhydrous dry basaltic melt. Uh, you should not expect much hydrous mineral out of the crystallization from that melt. Unless and until it has a little water content in the initial melt itself, that you can that you can generate by adding some serpentinized peridotite or by assimilating some serpentinized peridotite or serpentinite. By collapsing of the roof situation, you can conceive better in this way within the magma chamber.
Okay, sir. Thank you. Sir, next question is from Biswajit. The question is, with changing lithospheric thickness, does the mantle potential temperature also change?
No, it doesn't change much. Sorry, perhaps I was not clear enough in my talk. I told it. I tried to tell it actually. Let me come here. The slope of the geotherm means I wanted to mean the slope of the conductive geotherm is a function of the lithospheric thickness. Here it's a general scenario, 15 degrees centigrade per kilometer, but here it's the adiabatic gradient is 0.5 degrees centigrade per kilometer. You see here, the lithosphere is much thicker, but still the adiabatic geotherm is at the same place and with a gradient 0.5 degrees centigrade per kilometer. But this conductive geotherm it's changing. It's here it is 10.3 degrees centigrade per kilometer. And for thinner lithosphere,
Yes, sir.
sorry,
Sir.
for
Yes, sir. You're
okay.
right.
So perhaps you got the comment. Otherwise, I need to move to the full screen. Okay. For thinner lithosphere, again, you see here that conductive geothermal gradient has changed to 21 degrees centigrade per kilometer, keeping the adiabatic geotherm constant 0.5 degrees centigrade per kilometer. So with change in lithospheric thickness, we see a change in the conductive geothermal gradient. On the contrary, the adiabatic geothermal gradient remains the same. So that means in the asthenosphere, there is not much change in temperature with depth. There is a little change in temperature with depth, that is the pressure effect. As I told you, the asthenosphere is like a closed system because there is a lithosphere which acts as a thermal lid, as an insulator at the top. And in the core mantle boundary, there is there is a layer which acts as an insulator. So in between region, the mantle behaves adiabatically. So there will be no addition or removal of heat from the system. And as a result, the temperature changes very little with increasing depth. That is 0.5 degrees centigrade per kilometer. And it is almost irrespective of all tectonic setting. Clear?
Yes, sir.
Hello?
I think. Yes, sir. I think she has got her answer. Okay, sir. Moving to our next question. This question is from Rinita Rini. The question is, in case of subduction zones, the oceanic crust gets destroyed and asthenospheric mantle melts. Does the oceanic crust also melts here?
Could you please repeat it once more?
Okay, sir. In case of subduction zones, oceanic crust gets destroyed and asthenospheric mantle melts. Does the oceanic crust also melts here? The
Oh,
question
perhaps
is
not.
from Brinita
Per- per-
Devnath.
Perhaps not, because the oceanic crust, after dehydration, it becomes uh, so waterless. It is, and it forms eclogite, and it's a very dry eclogite, and perhaps it will be difficult to melt it. Rather, with continuous phase changes within that rock, it will increase in density higher, and it will keep on sinking within the asthenosphere without adding much into the melt being generated.
So there is a continuation of this question. Out of mantle melting and oceanic crust melting, which one gets priority?
Out of mantle melting, and
And oceanic crust melting.
obviously the dominant melt comes from it's being contributed from the mantle. So certainly the lion's share, it comes from the mantle. And the oceanic crust, subducted oceanic crust, it keep on sinking with continuous phase changes within it, following the Clapeyron equation you may be doing, and it increases in density and keeps on sinking within the atmosphere. Only the wedge of above the subduction zone, where the solidus temperature is drastically reduced, that gets the scope of partial melting.
Yes. So the next question is from Nilesh Banwal. He has asked, describe about fractional and equilibrium melting of mantle.
Yeah, actually, your question has a direct link with the mm, composition of the magma being generated depending on the mode of melting. Uh, as you rightly told, that there are two types of melting. One is the isobaric melting, and one is equilibrium batch melting, and another is fractional melting. So the basic difference is in fractional melting, you can conceive a situation that each droplets of melt is being generated, that is being separated out from the system. So you have to think of a system which is really that much porous that can extract all the melt being generated and keep the residue left over without any melt in it. This is one limiting case, and another limiting case could be you think of a system where at least 5% or 10% of the melting uh, becomes isobaric, means or it becomes equilibrium melting. That means the melt will be in contact with the residue, and after a certain pool of melt being generated, say 5% or 10%, that melt will be extracted out from the system. This is called batch melting, equilibrium batch melting. And the third extreme scenario is the entire equilibrium melting. That means you cannot take out the melt from the residue. And up to your desired level of melting, the melt and residue will be always in equilibrium with each other. That rarely happens. In most of the cases, it's a case of batch melting. It varies between equilibrium batch melting to your pure fractional melting.
Sir, thank you. We have, I think there are two questions more. Uh, this question is from Divya Nand Dubey. What is the role of water in mantle plume activity and how their work?
Yeah, it's a very good question because
Yes, sir.
I have talked about three types of melting. One is influenced by the plume. Uh, Next one is the divergent tectonic setting, and the third one is the convergent tectonic setting. In the case of first one, I have told that the only the mantle potential temperature increases. But at the same time, there is another effect which goes hand in hand. So, because of the upcoming plume, and which is geochemically a zoned asthenosphere, you can think, uh, zoned plumb of asthenosphere, where the upper part of the outer part of that plume, uh, once it starts to come up from that outer part of the plume, it already starts to metasomatize the mantle above it. So we have to really think of lowering of the solidus above a plume as well. So in that case, it will be just a combination of the increase in the mantle potential temperature as well as lowering of the solidus in that region. So it will be a combination between case 1 and case 3.
Yes, sir. Thank you. Sir, our last question is from Daniel Rabbani, Bacha Khan University, Charsada, Pakistan. He has
Mhm.
asked, Sir, how we compare the partial melting of intrusive rock with any other melting of rock? Mean geothermal gradients change the partial melting temperature.
Yeah, just tell me once more his good name and the
Huh.
question again.
Yes, sir. His name is Daniel Rabbani and
Okay.
he is from Bacha Khan University, Charsadda, Pakistan.
Okay.
And his question is, Sir, how we compare the partial melting of intrusive rock with any other melting of rock? Mean geothermal gradients change the partial melting temperature.
Yeah, Mr. Rabbani, the question, although it's not very clear to me, but here the entire discussion was related to, we were confined to the upper 200 kilometer of the mantle because crust is very negligible in thickness. So what we what I have tried to address here, all melting in all cases, it's a primary melting. But now you are talking about a male, which is a male from a intrusion or something like that. Uh, yeah, it's really not very clear. And would you please give one chance to make the question a bit
Okay, so
clearer?
we request,
Or
uh,
can you request him to
yes,
contact
sir, we
me?
are requesting him to write it once again. We
Okay,
are there. By then, sir, there are last one question.
sure.
Can we? Okay, sir. So this question has been asked by our Orghodip Dash from
Uh,
Calcutta University. He has asked why batch melting of ascending mantle can be approximated at asymptotic process.
yeah. So your entropy in that case, in the equilibrium batch, in case of equilibrium match melting, you have to think of a situation where the entropy remains the same. Otherwise, you can think of other process as well, like isocodic and those other processes. But this is a general practice. Mm, of course, thermodynamically very sound. That in case of melt modeling using software using softwares like P-melt, alpha melt, and this thing. It's a general practice, or that the thermodynamic system is taken as isentropic, where the entropy remains the same. Mostly in case of equilibrium batch melting.
Yes, sir. Thank you. Sir, he hasn't wrote it yet. So I think, yes, there is no question, no more questions. So thank you, sir, for answering all the questions patiently. We are
But
grateful to
maybe
you.
we are a bit pre-scheduled. Nah? You never thought of that. It will be only of half an hour lecture.
Yes,
But
yes,
as I
sir.
told you that I didn't want to involve the composition of the magma ecosystem, because once I involve it, I think I, I need to take a few more hours actually. And I am not good
but
in talking at length, as I told earlier. Okay, so
but
maybe I'm waiting for an opportunity, maybe in the next webinar, where I'll be
sure, sir.
dealing with.
We are really grateful, and sir, thanks once again for conducting this session in such a commendable manner. And now I would like to present the vote of thanks.
Actually,
Sir,
everything has been
sir,
compensated.
1 minute.
No, sure.
Deepmala, if there is any guest, if our speakers
Is
want to.
there any guest or participants who wants to share their thoughts or say a few words about our speakers and our event? Then they can they can write in the chat box, and we will unmute them. Is there anyone?
Now it's the situation like July 2020.
Hello, Obipsha or Natasha, should we wait or should
Yeah,
we?
I can wait. I can.
Okay, sir. Okay, sir. We are waiting.
Okay.
We can wait for 2 minutes.
Yes, sir. Yes, yes. So
Yes,
we
sir.
are
If
waiting.
anybody wants to talk
So
to
can I leave
Biswajit,
for 2 3 minutes? I'll be back within 3 or 4 minutes. Is it fine?
Sure, sir. We will wait.
Oh, sure.
So
Taposh sir is also present. Taposh
here, yes.
Bhattacharya sir.
Dr. Tapash Bhattacharya, our beloved sir is also here. So if any participants or guests or any students wants to say something, they can write in the chat box. We will unmute you and you can speak, or you can also put your message in the chat box, and if you put, we will read it on behalf of you. All the participants to stay here for 2 or 3 minutes more. Let sir back again, and we will start the vote of thanks. We will provide you the PPT and the feedback form by 5 p.m. today in the Telegram group. Please fill up the feedback form with your proper name, your designation, and name of your university or organization. Otherwise, we
Oh,
will not
yes,
be
I am
able
back.
to issue the certificates. Okay, sir is here again. Sir, I think there is no one. Actually, sir, there is someone asking a last question.
Sure.
Uh, okay, sir, we are taking that question.
Mm-hmm.
Sir, why does continental crust
Mm.
not melt? This has been asked by Piyu
No,
Shadukha GSI.
but this is not the case. Yes, there are specific sites where continental crust also gets melted. Otherwise, at least in Archean time, it got melted. Otherwise, how do you explain the formation of these TTG, tectonic areas, like 2009? Uh, yes, absolutely. This is not right. Actually, there are sites with introduction of volatiles or the uh, solidus temperature of continental crust becomes lower than the ambient temperature and it gets melted at places.
Okay, sir, uh, Dr. Robi Kumar Pandula from Andhra University, he has sent a message. I am reading on behalf of him. Today,
Hmm.
two sessions are very interesting and informative. Thanks for the organizer. Morning session is create new research in my mind. Okay, thank you for your kind words. Thank you so much, sir. Okay, sir, we are
So, okay,
moving.
please convey my regards to him.
Yes, sir. Thank you so much. Sir, there is a request. If our Dr. Tapash Bhattacharya, sir, uh, can say something at last. I mean, if he can give some concluding words before I start the vote of thanks. Hello, hello, Natasha or Obipsha, can you unmute, sir,
Yes, sir.
Dr. Tapash Bhattacharya?
Well, I think I
Yes, please.
already wrote back in response to Mr. Devaditya Bandyopadhyay's request. Isn't that right? Even before that, I wrote, I already talked for about an hour. So, warning that my is not working. Is that right?
Hello.
Moderators, can you hear me?
No, sir, your voice is not
Yes,
clear.
sir. Your voice is breaking.
Sir, your voice is not clear.
Can you hear me now?
Yes, sir. It is clear now.
Yes, sir.
Okay, the microphone even doesn't want me to speak because I already spoke for more than 1 hour. And so
Mhm.
I should not raise your boredom index. Uh, as Devaditya wrote, that I am that fittest person to conclude, that implies that as I spoke, everybody will leave. They won't stay anymore to listen to more. Well, I offer my thanks to the students. And when they were doing this organization, I once asked them, possibly a couple of evenings back, that whether these few faces or the few voices I am hearing, 4 or 5 voices, as if they are sitting next to next across a table and discussing and organizing. So I could not resist myself from asking, where are they? Someone is from Kolani, somebody said Shiliguri. I stopped asking the positions of the others. So that is a tremendous effect. I don't know if they have any other ex- experiences in organizing such things, but it's an Herculean effort, and they, to their surprise, found that the size of the enrollment increased so much that they have to change the platform. I was never aware of this live webinar. I knew about Google and other things, but this is a new realization, and I thank them a lot. It goes to show that if they are distracted from all the hillybillies of life in Calcutta, stay home, can do real great work. Okay, so I really thank them and I appreciate the cooperation. I am sure extended by the department, quote unquote, in exile because they all the professors mostly working from home. That's fantastic. The choice of topics, two drastically different. The first speaker only scratched the surface. And the scratches on surface doesn't last long because they don't go deeper. And the second speaker took us to 200 kilometers and assured that we will have a trip further down below next year. I really congratulate him for making the promise and making the first 200 kilometers so easily accessible and understandable. I could even feel the temperature changing because the lithosphere is thinning. It's fantastic. The visuals very few in number, but it perfectly matched what he is talking about, in spite of his repeated apologetic statements that I am not good at speaking at length. Well, the most precious things are very precise. So talking a lot may not convey a lot of message. So speaking a lot with a few words is the most important thing. I heard one person describing another person's ability to communicate. He says, he talks a lot but says a little. And here he talked a little but said a lot. So I thank him for his presentation. I thank the students for organizing it. And I thank all the people. This is a weekend, even if it's a lockdown, in between lockdown period, attending to the webinar, and not only that, posing very important question. I enjoyed equally. Can you hear me? The microphone is there or
Yes,
not?
sir. Yes, sir.
Okay, I enjoyed equally well the question answer session of Dr. Ghosh. And I find he has mischievously hidden the treasure he has. Unless you poke him, you will never know it is the serpentinized mantle that gets inside the magma chamber to supply the water to form the amphibole, which was asked from Japan. They are sitting on top of magma chamber, possibly. So now we know that. And this discussion, I wish could have continued further long, but whatever little came out of it, I think I am greatly enriched and I am benefited. And I also love to express my warmest regards, I underline regards, to all the organizers and the listeners. Thank you.
Thank you so much, sir, for your wonderful conclusion. And we, the student of Calcutta University, we offer our humble regards to both our respected sirs. Thank you so much for encouraging us and giving such a wonderful lectures on this fabulous topics. Okay, sir, would you like to say something?
Yes, the last single line, maybe.
Yes, sir.
My profuse thanks to the all in the audience, and my real hats off to the those in the organizing group. Stay well,
Thank you so much.
stay safe. Thank you.
Thank you so much, sir. So now
And of course, just I missed
yes, sir.
something.
Sure.
Uh, actually, please, with this, I want to convey my pranam to Tapas Bhattacharya sir for saying very nice words about me. Thank you, sir.
I seldom lie. Yes, please go ahead.
Yeah. Thank you so much. Now I will present the vote of thanks. I congratulate all the members and participants and especially our honorable teachers to make the event Ignite 2020 successful. We received an overwhelming response from geology enthusiasts all over the country, actually across the country, I guess. So, for which the team Ignite 2020 will always remain thankful to them. We do not have words to express our deep gratitude towards towards our professors, especially for their help and cooperation towards this event. in between their busy schedules. It perhaps the best gift to the student on the occasion of Teachers' Day. We seek their blessings for conduction of more such events in future. Thank you, sir. And a special thank to some of our seniors for their cooperation in this event. Thank you once again. Thank you all the participants for joining us. We wish your safety and good health amidst this pandemic. Thank you.
Okay, with all your permission, I should leave now. Thank you. Thank you.
Thank you, sir.
Okay. Yeah.
Yes, I am ending the meeting. Thank you.
Yes. Thank you, participants.